If you want an example of when an inelegant solution is the best one, let's go ahead and do find all anagrams in a string. Given two strings, S and P, return an array of all the starting indices of P's anagrams in S. You can return the answer in any order. An anagram is, okay, yeah, you know what an anagram is. So to give an example, this one, so the starting indices are 0 and X, A, B, C. These first letters, you can clearly see, are A, B, and C. And so 0, 1, 2, 3, 4, 5, 6, B, A, C. Okay, there's another one. And another thing to note is in the second example is some of them can overlap. So for example, you've got AB, you've got AB, and then in the next, you shift one over, you've got BA, and that's still an anagram. And then the next one over, AB, that's still an anagram. So you're going to have some overlap. So I'll go ahead and talk about what kind of the typical solution is. So, all right, you know something, an anagram exists when you've got some span, some window within the word, it's contiguous. And if all the letters are the same as all the letters in our target reference word, it's an anagram. And then you'd add the start of that window to your output. The reason I don't really, there's a trade-off here between getting some like what I think would be a little bit more of an elegant approach with very inelegant syntax and some kind of implementation side effects that make it less worth it than it seems on its face. So there's kind of two things you can do. And they're both very similar, so the difference is really in the implementation. You got this target word P, and you can condense it from a single word with potentially repeating characters to an array where you have the counts of each character. You can implement this array as either a hash table, so in C++, that's an unordered map, or as just like an actual array where the indices correspond to certain letters. So this really hinges on, the array approach hinges on the limitation listed here, which is that the reference word is all lowercase English letters. So there are 26 of those, and no more, no less. So your array would be 26 entries long, versus if you did a hash table, maybe that would be more maintainable in that you could expand a hash table to cover other kinds of characters without having to like change it too much. Or for the purpose of an interview, it would be easier and cleaner to write and fewer lines of code to use the array approach. And the reason for that is because in C++ and, well, really a lot of languages, you can just do this between two vectors. You can use the double equal sign, and it will compare every entry index by index. Now, you could do that with a hash table too, but then the benefits of that would be, okay, the hash table may be a little smaller if the reference word doesn't have all 26 letters, but if it does, then you're kind of back at where you started. I'll just go ahead and start instead of rambling on about the entire thing from up front. So we need first a counter. Actually, no, well, while we're here, I'm gonna check for edge cases. So edge cases, for example, if the main one will probably be if our reference word is longer than the actual input string. Well, there's no way that there could be anagrams. So it's just something to check for. I guess realistically, that probably wouldn't affect. It might actually, because then you're gonna okay. If it's impossible to have a window, okay, anyway, I'm jumping around, but let's go ahead and write this edge case. So if s.size is less than p.size, return an empty array. All right, so now we actually need a return vector. So vector int return And then we also need a window. So do I need a window? No, no, no. Yes, wait, I gotta think this through. Okay, we need a word bank. The bank is gonna be our available characters. So this is the counts of this thing in NP, and that's gonna be 26 letters long. I can never remember what the order of this allocator is, on if it's like size first and then what you fill it with, as opposed to what you fill it with and then size. I'm pretty sure it's size first. And then what else? I guess realistically a window. Window. So window 26. Hard coding assumptions. I don't know if it's I don't know if there's like an elegant way to say like the size of the lowercase ASCII characters and like get it from some kind of code source. But right now we're going to use a magic number. It's a magic number. Okay, and then we need a main for loop. Okay, and why we need a for loop? Because the overall approach is a sliding window, which at a minimum is going to be linear. You've got some window of size that, and you're sliding it across. Suppose the input character, the reference word is just one character. Then your window is going to be one. You're going to have stride of, well, you're always going to have stride of one, and you're going to slide it across the input word, which is unsorted. So there's no like logarithmic search you can do. It's going to be linear. That's our lower bound for our runtime. And indeed, using this approach with the word bank, it's going to be that way. And if you're picking it up already, so this word bank is 26 characters long, entries, and our window is 26 entries long, and we have a stride of one in our loop. Well, don't we have to compare this bank to the window at every step? Yes, we do. But that's still going to be constant time because their sizes don't change with respect to the length of either of these inputs. And I'll talk about some alternatives to this that are worth considering in later on. So let me go ahead and keep going. And well, actually, what do we got to do? So we got that. Let's populate the bank. So populate bank for character C in P bank. And then how do we do this? We do C minus A. And then we increment it. So what this is doing, and this is why this solution's kind of inelegant. I'm not a fan, but it works out to be cleaner for interviews and like compactness and outlines of code. What this is doing is the standard ASCII character set or UTF-8 or what have you, at least for these like first 7 bits of characters. It's assigning characters as numbers. And what you have is, at least for the stretch that corresponds to the lowercase English characters in ASCII, it goes in order. So A, and then B, and then C, and then D in increasing order. So the letter Z is exactly 25 past the encoding for A. So 0 to 26, they're not actually, it doesn't start at 0, but what matters is a difference. So if we take whatever character it is, however many characters past A it is, we can treat this like an integer. We get our index into the array. I'm not a fan of that because that's not super easy to do in every single language. Some of them won't let you do that at all. C and C++ certainly do. And so if your language doesn't let you do something like this, then you're stuck with a hash table based approach. All right, so we've got our bank populated. And since we're doing a sliding window, let's go ahead and populate let's go ahead and check the first window because we're not going to have our index start earlier than 0. And we're certainly going to need to know where the end of the window is. So first window for, I'm going to need indices this time. So let's go back to a regular for loop. I equals 0. I is less than size of p, because our window is the size of p. What do? We need to detract from our bank because we are consuming a character, so we need to know when there's none left. So bank si, so the character, corresponding character from s minus a, get the index, and x equals 1, and we are adding it to our window. So window si minus a equals 1. And if you'll notice what I'm doing here, I'm combining two statements behind a single semicolon separated by a comma. That is allowed. That's not good coding style. So if you do something like this, you should call it out in your interview and say, hey, is this okay? Or would you rather I just stick to using braces to combine the elements in the loop? This removes the braces. I think makes it a little easier to read, assuming you don't need to change it. It's certainly a little less maintainable. So do it, but call it out if you do. So we got our first window. So now we need to do sliding window. And actually, let's check if this first window is part of, let's see if that first window is actually an anagram. So if, and here's the key. If window is equal to the bank, then we add it to our output. So ret for return. The start of the first possible window is, of course, index 0. And this is why I think this vector approach is okay, because this is an easy, very quick way to write out comparing two arrays instead of having to do it in a stinking loop. Yeah, this is why I think this approach is kind of preferred. It really cuts down the time to actually implement it. And, when time's of the essence, sometimes the interviewer might actually prefer that you use the faster to code, but maybe less proper solution for the sake of time, because that means, as an engineer, you're going to make trade-offs, time and cost versus how good the solution is. And sometimes the worst solution is valid because it's faster and faster means cheaper. So I don't know. The trade-off. It's a trade-off that's worth discussing. All right, so sliding window. So for int I equals, and this time we are starting at the end or one past the end of our sliding window. So p dot size. Let's go ahead and add space there since it's not some little integer. I is less than s dot size, and then increment. And for this one, I am going to use the curly braces because it could get weird. Okay, so we're starting one past the end of our window. So what I'm going to do is remove and add from the bank and window. So let's see, bank. Let's see, bank s. We're adding the next element. Sorry, let's first remove the next element from the bank. So minus a, next coming character. Let's see. So we got this bank, and we want to add the character we just removed from the bank. So bank. Actually, let me think. Do I ever want to adjust the bank? No. Okay, I was getting, let's see. Maybe I don't want to do this because the bank I want to keep constant. And then the window is the only thing I'm going to update. Yeah, okay, that makes more sense. So first we populate the bank from this, and then we populate the window, and then we compare if they end up being the same because we are destroying the positional information and keeping only the counts, which is fine for anagrams because that's the definition of an anagram. All right, so bank and window, and then we compare. We'd only want to detract, like subtract things from the bank if we wanted to check if the counts were 0, but we're not doing that. We're doing the window approach. Okay, that makes more sense. Okay, window. So we're going to add the latest character to the window, and we're going to subtract the old character that comes out of it from our counts. So window si minus p dot size. Do I need to add in another? Let me think. So suppose we are dealing with a stride of 3, and when this is our first window. So now we want to take one stride, BAE. We want to add E to our window. Okay, that's fine. This takes care of that. And we want to subtract C. So we're at E, so our index is 0, 1, 2, 3. We want to get 0. So 3 minus the size of P, so 3 minus 3, 0, 1, 2, 3 is 0, so index 0. Okay, I don't think we need this. So we're at index 0, 1, 2. That's fine. That takes care of that. 0, 1, 2, 3. 3 minus the size of our, yep, okay. Let's go ahead and keep it that way. Subtract it from our window. And now we're going to compare the window and bank again. Dot pushback. And this time we're pushing back the start of our current window. So I minus p dot size. And this is what I was thinking, well, so we first wanted to remove index 0 from our window, but now if they're the same, we want to add index 1. So this plus 1. That's fine. That's what we want. And then turn the final output. So let's analyze time and space complexity, and then I'll talk about kind of an approach that I think might be a little better, but kind of trickier to implement. And I think since it doesn't change the theoretical bounds, this is what I would probably do for an interview case, and then I would talk about maybe the other solution that's a little finickier to implement and riskier. Finicky means risky. All right, so edge case, this is a constant check. These are readily available by the underlying containers. They don't have to do a linear search to find out, so that's constant. This is allocating constant space. It's size of 26, so it's not a single item, but it's not going to change regardless of the input. So this is constant space. We've got a linear loop here because, so what if P is the same size as S? Well, it could be. We've got this edge case covering if P is longer, but if it could still be up to the same size. So that's linear search. This is, again, linear. So if they're the same size, that's another linear time, not allocating any extra space. The return statement is potentially linear space. It depends if you want to count it or not, but this output scales linearly with the size of the inputs because it could potentially be, well, what if an anagram starts on every single index, as in this example, every single index minus the difference in size between them. So if, for example, every letter is the same and your reference word is a single letter and it's that letter, then your output is going to basically be every index of your input. So that is linear. This loop is linear because, again, suppose your reference word is size 1, so your window size is 1, and you're sliding across the entire word. That's linear. Not allocating anything except output space. So that's total is O of n time and O of 1 space. And the key is that these two, even though they're arrays, they're vectors, they're of size exactly 26 all the time. So this is a constant check. Yeah. All right. So the other approach that I think would be better is realistically, instead of tracking the counts of every single letter, okay, you do need to make, say, a set, I suppose. You do need to find like initial counts of the letters that are in this. But, okay, if you had a bank, you still have this bank object, but instead of an array, it's a hash table. And it's keyed by the characters. So then the values in this hash table would be the counts of those characters. You could gain back some real world memory potentially. Well, the hash table could it could be less than 26 entries. But that said, it's a beefier data structure, so you're probably not going to have any real savings there. Where the real savings would be is maintainability if you were to expand beyond lowercase ASCII characters. And you're to have other characters. There's UTF-8, which is, a variable length encoding scheme. UTF-16, 32, 64. There's a lot of characters out there. There's a lot of languages with some weird squiggly lines that mean things to, a lot of people. And you can't fit all that in the 127 range that is ASCII. So you need more characters. So that'd be more maintainable to use a hash table. And then you'd have to loop through the hash table and compare the counts of all the things in the bank. Now you could do that. You could potentially, I think if you were to keep track of two integers, one is the amount of remaining entries in the bank. So the sum of all the counts of the characters, so just when it's full, it'll be the size of p, and when it's empty, it'll be 0, and you have to do some checking accordingly. Unlike, okay, we can't add more than that. We can't add more than size of p items to the bank. We can't have less than 0 in the bank. And then instead of a window, you're incrementing and decrementing counters. So the count of the things in the bank, and then you also need to keep track of intermediary letters that are not part of your reference word that are in your window. So if that counter is ever not 0, so if it's greater than 0, then you would not add an output. You would not add an index to your output. So for example, you got this window BAE. You need a counter, so you'd have one that says 2 because you've got B and A. Wait, your reference is 3, so 3, and then you subtract these two, so your in window counter, your in reference counter would be 1 because it's 3 minus 2, and then your out of reference counter would be 1. Both of those would need to be 0 in order to add something to your output. I think that would be better. I haven't fleshed it out so much, and it's kind of finicky. So like I said, I like this approach better for a code compactness point of view. Let's go ahead and do an example. I'll do this one, I guess, because I think it covers the cases where letters are not in your window. All right, so we got this. And then we've got our array, so bank, window, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I'm going to copy and paste that and hope it's 26. I'm not going to go through and count them all, but I think it's probably fine. All right, so bank and window, we allocate those. This edge case doesn't trigger because our size check is fine. Populate the bank. So for a character in P, we've got A, B, and C. First three letters, thank goodness. So we've got 1, 1, 1. We've got one character of each. And then we're going to check the window. So we've got our window, our first three letters, C, B, and A. So C, B, A. It's in reverse order. Do the window and the bank, are they the same? Yes, yes they are. So return, we're gonna have 0. Now let's check here. So our window is now, I'm gonna go ahead and I'm gonna add spaces, I guess, for the windows. So first we were here, now we are here, BAE. So what we wanna do is the character, our new character that we're adding, so E, we're gonna increment that. So A, B, C, D, E, fifth one. So we're going to increment that, and we're going to decrement the character that just went out, so C. Is that part, our window and bank the same? No, they are not, so we continue. So then that, B goes out, B comes in. Well, that makes it easy, so our window is actually not going to change. So for example, B goes out, B comes in. Windows are not the same. Let's continue. That, so A falls out, A comes in. A comes out, A comes in. They're not the same, so we continue. Now it's going to get a little more interesting. So E falls out, B comes in. So E falls out, or actually, I'm doing it in opposite order. I should be adding first. So B comes in. So that comes in, and then E falls out. What do I do? Are arrays the same? They are not. Continue. B falls out, A comes in. So as far as I should be adding first because that's what the algorithm does. So we've got A coming in, and then B fell out. So that's back to 1. Our array is the same. Oh, did I miss? I should have 3 letters. A, B, A. What did I do? Oh, wait. Yeah. A comes in, and then a B fell out. So this dropped from 2 to 1. Arrays are not the same. Am I missing some zeros? I erased a couple of characters. Arrays are not the same. Let's continue. All right, so C comes in. C comes in, and A fell out. Our arrays are, again, the same, so let's go ahead and add the index. We were at index 0, 1, 2, 3, 4, 5, 6, 7, 8? Index 8. Is that right? 0, 1, 2, 3, 4, 5, 6. All right, one at the start of the window. So 0, 1, 2, 3, 4, 5, 6. Yep, index 6. So that happened. And yeah, so index 6. So for example, this I counter is at 9. No, it's at 8. So 6, 7, 8, 8, 7, 6, 5. So subtract 3 because it's the size of our window, and then add 1. So that's this calculation there. Subtract 3, add 1. Yep, okay. Let's keep going. D comes in, B falls out. We have A, C, D. So D, A, B, C, D comes in, B falls out. Our windows are not the same. And And I think that's the end of the window. There's no more window. That's the last iteration. We break out of the loop and return this. We return 0 and 6. That is our expected output. And I think that's good enough. Let's call it good. Give it a run for syntax. No, what'd I do? Less than 1. Oh. Yep. Maybe that's an issue. I did that here too. Why did I type that? It should be incrementing I. No. Am I getting some array math? Out of bounds. Where does it say? Does it say? Shadow byte. I don't know what that is. All right. So what are we doing? Oh my gosh. Yeah, that's why. Should be subtracting a from this window to get something between 0 and 26. I don't know why I subtracted off p.size. That's not correct. That will give you something wrong. Why am I adding every single one? If window is equal to the bank. Oh wait. Bank. I want to subtract the thing that. Oh, that's why. Okay, so minus size. That's what I needed to do. All right, so this gets this index, but now we need to go back to, okay, what am I doing? No. This should be subtracted from I. So the window, we've got our character in S, but we want to go backwards in S to get the correct character. And then we translate that into an index using subtracting A. So, okay, that's finicky. That was an issue. Hopefully this works now. Cool. There we go. That's what I'm talking about. All right. So yeah, he was shifting the correct things, the correct places. Yep. Submit it. Cool. All right. Well, anagrams in a string. Check and done.